Here's something else that's kind of fun. Let's use the product rule and the chain rule to derive the quotient rule. Let f of x equal g of x over h of x. There's a few different ways this can be done. I want to use the product rule and the chain rule though. So what I'm gonna do to help me do that is I'm going to rewrite this fraction, g of x divided by h of x, as g of x times the reciprocal of h of x to the -1 power. Notice that's a -1 power, not an inverse function. Those are different things. I got the -1 there, not above the h. It's not an inverse function, it's a power. That's now the product of two functions. If I assume these functions are differentiable, I can use the product rule. And then when I differentiate the second one, because it's a composition, h of x is the inside function and raising to the -1 power is the outside function, I can use the chain rule. Let's see what happens when I do that. Product rule first. Left and right functions. Left d right. I don't want to take the derivative yet, so I'm doing the d dx thing. Lots of parentheses, but they're all worth it. Left d right plus right d left. What's the derivative of the left? The g? It's just g prime. By the way, I used parentheses there around the g, but I didn't have to do that. Those parentheses are optional. All right. Not done taking derivatives. I need to take the derivative here with the chain rule. The inside function is h of x. The outside function is x to the -1 power. You got to think in terms of order of operations with how you use math symbols. H of x quantity to the -1 power. When you plug a number in for x, you first evaluate the function h, and then you raise the result to the -1 power. So what's the derivative? The outside function is x to the -1 power. I'm not actually going to write that down anywhere. I'm just going to imagine it. X to the -1 power. If I differentiate that, that's how I use the power rule. I bring the -1 down in front. Then I have x to the -1 minus 1 power, x to the -2 power. But don't write x to the -2 power because you got to plug h of x into that in place of x. Write h of x to the -2 power. Then don't forget, extra step, multiply times the derivative of the inside function, which is h prime. The second term I'm going to write as a fraction right away. Oh, a little simplification. I can write the first term as a fraction as well with a minus sign in front. Is this starting to feel like we're getting somewhere? I do see low d high minus high d low over the square of what's below. I do see the square of what's below there. Yeah, that looks good. I want to add the fractions to write the answer as one fraction. I better get a common denominator of h of x quantity squared. So I got to multiply this one by h of x divided by h of x, which is okay because that's a disguised form of 1. At least wherever h of x is non-zero. So I get g prime of x times h of x divided by h of x squared. And these now have a common denominator of h of x squared. Combine them into one fraction. And maybe rearrange the sides these are on. Low d high minus high d low over the square of what's below. G is the high function, h is the low function. Low d high minus high d low over the square of what's below. I think that's pretty cool. Fun to use the product rule and chain rule to derive the quotient rule. Is this a proof of the quotient rule? Well, yes, if you believe the product rule and chain rule are true, then you can do this proof of the quotient rule. Though I didn't write sentences, true proofs are arguments, so they involve sentences. You would say things like, well, by the definition of F and the product rule, I can write this. And then by the chain rule, I can do that. And then you'd say by algebra properties, you can do the rest. And it probably would be good to mention all this is assuming h of x is non-zero, so I'm not dividing by 0. That is a necessary assumption.